Thank you very much, Julian, and thank you for inviting me. It's an honor to be here. Well, you know, this is a talk on the interplay between natural intelligence and artificial intelligence. And I'd like to start with the toughest slide in order to summarize what I'm going to talk about. Let's say that if you're an applied mathematician, you want to solve a problem, no matter which kind of problem. Here I generically call it physical problem, but not because it comes from physics. It could come from physics, but it could also come from engineering, it could come from medicine and many other fields, say. So if you want to solve a problem, perhaps the most natural and traditional way is to go through this left branch, namely try to understand the problem and to set up a so-called mathematical model. Mathematical model means describing these problems in mathematical terms. So this is the realm of mathematical physics and the mathematical analysis, basically. And most often, these problems here, you cannot solve them by paper and pencil. You don't have an exact solution. You need to use a computer. Not because computers are more intelligent than mathematicians, but just because you want to introduce a new problem, which is an approximation. We can call this approximation generically a digital model. And this is a finite dimensional problem, namely a problem that can be solved by a computer. So in the end, you will have a solution that we can call a digital solution. And this solution, as you see, is strongly rooted in a mathematical understanding of the physical problem. So basically, there's a lot of theory behind this. There's a lot of physical theory, understanding of the problem, and mathematical theory, and then numerical theory, or theory of algorithms, say. Now, more recently, we have been exposed to a completely different kind of paradigms. Namely, forget about theory, just use data. Data means experience, as we'll see. And with those data, we try to set up algorithms that will extract information from those data. And in the end, delivering a solution, which is just driven by data and not by theory. So this is an alternative approach, which is, say, in the realm of AI, artificial intelligence, as we'll see. Now, I believe that in the future, we'll be more and more sitting on this type of paradigm, namely merging the two approaches, try to take advantage of both of them, taking advantage of the theoretical knowledge that we have, and on the other side, by the big amount of data that typically we have available, and extracting the best of both approaches, say. This is what is today called scientific machine learning, or more generally, scientific AI, right? So I will try to go first on this side of the diagram, and then on that one. And to be more concrete, I try to provide a specific example of the way you can set up a mathematical model for a given physical problem. So let me first give the general picture. When you use a digital model, as I was saying before, you have a physical problem. The solution is not known. You can only measure some component of the solution at a very high cost. You replace this by a mathematical model, namely by an equation or a set of equations where you have data and you have a solution. And mathematicians typically indicate the solution as U, unknown, right? And of course, you make an error, and this is the modeling error. Then you translate this problem into an approximate problem that you could call numerical model, and then your solution will be UH, say, an approximation. And of course, this comes with an approximation of the data as well. So instead of DH, instead of D, you'll have DH, approximate data. So you have a new problem that you can solve by an algorithm and by a language, say, on a computer, and getting the solution that you can call UC. Eventually, this is what you get. You computed, right? So you have errors that you make here. This is the modeling error. You have another error that you make here when you approximate this problem, which is unsolvable, by a problem which is solvable. And then you have another error, which is due to the fact that when you use a computer, we are using finite dimensional arithmetic, not exact arithmetic. So mathematicians should be good enough to be able to control all these errors and to keep them under control in order to deliver in the end a solution which is trustable. And I want to show you one example, which is a very complex example. And this example is a digital model for the heart. So first of all, what is the motivation? The motivation is the fact that when you collaborate with doctors, you discover that one of the big killing factors are cardiovascular diseases. Cardiovascular diseases are responsible in our countries, in Western countries, in Europe in particular, for, say, many, many deaths. And it's on the order of 42% of all deaths that are due to cardiovascular diseases, much more than those due to cancer, say. So cardiovascular diseases have different type of forms. In particular, heart failure is one of the most responsible. So what we wanted to do was to study the behavior of the heart and try to model its functionality using mathematics. And in the end, delivering this information to doctors and to the cardiologists, and then enabling the cardiologists to have a better knowledge of cardiovascular diseases, say, and helping them with therapy, but also with surgery, try to devise optimal surgeries, thanks to mathematics. So before doing that, you have to understand the basic physiology, right? So understanding basic physiology means to go into the very nature of the heartbeat. Of course, the heart is beating because it is a pump. This is very often said, right? But a pump needs an energy, right? So if it's an electrical pump, of course, you have to plug into the electricity. If it's the heart, the pump is pumping because of the fact that the heart is subject in every second of our life to an electrical stimuli. So we have an electrical stimuli that takes place in a very specific position of the heart. It's called the sinuatrial node. It's the upper right atrium, say. This generates an electrical field. So this is the so-called electrophysiology component. This electrical field then reaches every single cardiomyocytes, which are the basic cells of our heart, and it generates force. And this force is only due to the presence of the electrical field, say. Then this force is generated by the fact that in every cardiomyocyte, there are channels that open and close. And there is a, say, transition of ions, of calcium, of phosphorus, of potassium, from the inner side to the outer side, say, through the membrane. So this creates a so-called transmembrane electric potential that generates this force. But this, say, aggregation of all these forces allows the heart to beat. So you have relaxation and contraction. So you have the mechanics of the tissue. But then, within the atria and the ventricles, you have the blood. And therefore, you have the blood dynamics. You have the dynamics or the hemodynamics of blood due to the fact that the heart is pumping, right, and relaxing. Then you have the perfusion of the myocardium, which is due to the presence of the coronaries. Then you have the dynamics of the valves. We have 4 valves in our heart. And we have the connection with the external circulation. So all this is the conceptual physical model of the heart. And when you go through all these steps, all these physical processes, you can end up with a kind of monster system, which is a mathematical system. And this is actually the heart, seen from a mathematician, right? So, of course, I'm not going to explain those equations, but every equation represents a physical process. This is the cellular ions dynamics. This is the contraction of the cardiomyocytes. This is the electrophysiology, namely the generation of the electrical field. This is the external circulation. Those are the equations of fluid dynamics, of hemodynamics. And this is for the mechanics of the deformation of the heart, and so on and so forth. This is for the ECG, the electrocardiogram reconstruction, and this is for the myocardial perfusion. Now, all those equations, for those who are in the field of math are partial differential equations, almost all of them. And they are nonlinear, and they are coupled together. So if you can solve this set of equations, then you are able to solve or to reproduce the hard functionality. Now, of course, I'm skipping all the infinitely many difficulties that are behind this solution, but let me try to convince you that what you get is actually an accurate reconstruction of the hard behavior. So this is the heart of a young man, say a young American, 20-year-old. So you start from this very geometry, and what you see here is the creation of the electrical or the electric potential. This is called electrophysiology. Now, this is time. We go from 0 up to 8, which means 8/10 of a second, which is a complete heartbeat. So you start here, you see, with the stimuli. The electrical field propagates first to the atria and then down to the ventricles. And this is the electrical front of propagation of the excitation, say. So you have a scale here where you have values. And basically, in every single point, we have specific value that is changing in time. So this is something that you will never be able to get at the clinical level. You don't have this type of information at the clinical level. So this is something which is quantitative from one side and also dynamic from the other side. So you cannot find it on an atlas, say, on a medical atlas. So this is something that interests the electrophysiologist, those interested in the rhythm of the heart, and the pathologists due to the rhythm of the heart. This is the heart beating. What we are computing here, thanks to our model, are the forces, electrical forces, that are generated at every single cardiomyocyte, at every single cell. Now the scale is in kilopascal, right, for ventricles and for atria. Now you see the heart beating from the outside, right? So here is the right heart, right ventricle, the left ventricle. This big tube is actually the pulmonary artery that brings venous blood to the lungs. It releases the CO2, it intakes the oxygen, and then the oxygenated blood goes back to the heart through 4 arteries, which are called the pulmonary veins. You see 2 of them here, the 2 others are hidden there. So the blood, oxygenated blood, goes into the left atrium and then down to the left ventricle, and then is pumped into this big tube, which is the ascending aorta, and through the ascending aorta is reaching all the rest of our circulation, say. So what is reproduced here in different colors is the D stands for displacement. I mean, the displacement of the heart. You go from 0 to 2 centimeters. So for an adult, the diameter of the heart is of the order of 8 centimeters. So 2 centimeters, which is the maximum displacement, is of the order of 25% of the displacement. So there's a very big displacement, say, from the physical point of view. And what you see here is the heart seen from the interior. Now you see the fluid dynamics. You see here the valves. This is the mitral valve that connects the right atrium to the left atrium. This is the pulmonary valve that connects the right ventricle with the pulmonary artery. And there you see the big aorta, and this is the pulmonary artery that you have seen before. And what you see here is the blood dynamics. Now we are reproducing the velocity magnitude on a scale that goes from 0 to 1.4 centimeter per second. And what you see here is just a detail. Please do not forget this is a healthy heart. It's a heart of a young people with no diseases. So what you see here is the left heart, and you see the formation of the big vortices. So this is a repeat in an healthy situation. Now in an unhealthy situation, of course, the pattern would be different. But I wanted to show the complexity of these different physical variables in a single heart beating, say. So there's nothing to see with AI so far, with artificial intelligence. This is simply deduced by basic knowledge of heart physiology and then mathematics, right? Mathematics, translation, and numerical solution. So now we go to the right-hand picture. You remember the AI picture. So I'd like to introduce the AI now, and I'm making a few remarks on the AI. And in the end, I will try to merge the 2 approaches, the one based on physical understanding or natural intelligence, say, and the other one based on artificial intelligence. So what is artificial intelligence? Well, artificial intelligence is a big word, say, that encompasses many different things. First of all, it's an old story, because the very first definition was given by, at that time, a young mathematician, John McCarthy. This was 1955, so more than 70 years ago. And he defined artificial intelligence as the science and the engineering that make machine intelligent, right? And actually, what counts here is the fact that machines means computers basically, right, behave as if they were intelligent. There is no definition of natural intelligence in all this business, but the focus is on the behavior of systems, of machines, in solving specific tasks. So today, 70 years after the definition, where do we stand? You see here this kind of onion with different layers. The most, say, external layer is the one of the application. So today, artificial intelligence is used in the robotics, in the expert system, in the computer vision, in the natural language processing, in the dialogue, say, in the speech recognition, and then in industrial level, in planning and scheduling, in representing the knowledge, and so on and so forth. Or autonomous driving, for instance, and many other fields. This is where you find artificial intelligence algorithms, say. But how does a system, a machine, become intelligent? Well, by learning. And this is the key word. And that's why we have what is called machine learning. So machine learning is the process by which a machine can learn autonomously without being programmed for that, right? And there are many different ways of learning and many different tasks that we'll try to revisit shortly. But how is that possible that a machine learn? Well, this is thanks to math, basically. They need algorithms for learning. And there are many different kinds of algorithms, but today the most successful ones are the so-called neural networks. And I will talk about neural networks in a while. So neural networks are the basic engine of machine learning. And machine learning is what, allows a machine to behave in an intelligent way, say. And there are many different kinds of neural networks. In particular, those who are very effective today are the deep neural networks, and this is why we talk about deep learning. And generative AI is one specific example of deep learning. Generative AI is the one that is behind the so-called large language models, which are those that allow machine to create a dialogue with us, like with ChatGPT or DeepSeek or other things like that. So this is the global picture, say. So machine can learn. So we need a definition for learning, right? I mean, mathematicians, need definitions. And there are many definitions of learning. And this is the one that I think is the most accurate, or the one that I like the best. And this is due to Tom Mitchell, say 1997, long ago. And he said that a computer program is said to learn from an experience E. So it's not learning from theory. There is no theory here, right? It learns from an experience E with respect to some task T. So learning is in order to address a specific task, and some performance measure, P, if its performance on this task, measured by P, improves with experience, E. So I want to poorly translate it in these terms. The more data you have, the more experience you have, the better will be your performance, the performance of your machine when learning. So basically you are driven by data, and data is what is encoding the experience in any specific task, right? Any kind of task. So as you see, you have some elements here: experience, task, and performance measure. And let me show a very simple example, right? It's very simple. the learning process can have can produce different type of achievement. One of those is classification. Classification is just one way to learn. What does that mean, classification? It means that you want to classify objects or things, right? As in this case, you want to be able, you want your machine, your system to be able, for instance, to recognize a dog. And so how do we allow the machine to recognize a dog? How is the process? Well, it's a very natural process, the one that allows kids to recognize dogs or cats or birds, for instance. What do we do with kids? If you have a child or a grandchild and you want to teach him or her what is a dog, right? You don't give him or her a definition. You don't say that dog is an animal, is a mammifer. This is useless, right? You take him or her to the park or to the street and you meet a dog. Maybe you say, well, look at the dog, right? And maybe you also say, wow or bow, right? And after a while, and this is the experience, right? We meet 10 times or 50 times dogs, different dogs. This is all the experience. And after a while, we encounter a new dog and the little kid will say wow or bow, right? And we will understand that he or she understands how to recognize dogs. So we have experience, the amount of, all the times that you have been meeting a dog. You have a process that takes place in the brain of the kid, very complex, right? And then you have the solution, the output, recognizing the dog, right? And you want to replicate this process. So no theory, no definition on dogs, right? So what do you do? Well, instead of taking the machine and bringing the machine to the park, right? You just give the machine a series of pictures, right? 100 pictures. And you may have dogs or cats or birds or houses. And we supervise the machine. And we put, for instance, 1 on those pictures that correspond to dogs and 0 otherwise. This is the way we train the machine. Just as we train our kid when we take him or her to the street, right? Then, instead of a brain, we need a model. We need a mathematical model, right? We need a mathematical model. So the training set is the set of experience, right? The number of, you see here in this notation, we have capital N pictures, and for every picture, they may represent dogs or other elements, and this is our evaluation. We label it as 1 or 0. If it's a dog, 1 or 0 otherwise. Right? This is the experience E. The task is to recognize a dog. And recognizing a dog means that your machine should be able to put on every single picture 1 if it is a dog and 0 otherwise. And what is the model? The model is just a function, namely a map that translates a new picture, x, into a new answer, y, 0, 1. So this is the model. And this is actually surrogating the presence of the absence of the brain. Instead of having a brain, you have a mathematical model. And these W are parameters that the machine should learn. This is the learning phase. Learning phase means being able to determine those parameters that identify this model. And the way the machine chooses those parameters is through a mathematical minimization step. Namely, you have a function that basically estimates the number of errors or the errors that your machine is making when evaluating these pictures. And when you minimize this function, you find these the optimal weights that are then belonging to the mathematical model. So you have the task, you have the experience under the form of data, you have a model under the form of mathematical function, and you have a performance measure, which is the one that consists in choosing this function that measures the error, say. And of course, one of the very big tasks is how you compute the minimum of this function. You need an optimization algorithm, minimization algorithm, and this is extremely expensive, and this has to see with the sustainability of machine learning algorithms today, because these models, especially when you use large language models for the dialogue like in ChatGPT, these models may consist of thousands, of hundreds of thousands, sometimes millions of parameters that you want to minimize. So this means that you want to minimize functions that are living in spaces of very high dimension, order of millions of dimension. And you know that minimizing functions, even in the two-dimensional space or three-dimensional space, might be very difficult. But in this case, it's particularly difficult. This is where you spend, you invest in a very high amount of energy, say. So this is the idea. Now, what can you do in machine learning? What kind of learning and what kind of experience can you have? How can you assist? How can you train the machine in order for it to be able to learn? Well, basically in at least three different ways. The first one is supervised learning, right? As the example that you have seen before. We provide 100 pictures and we label those pictures with 1 or 0. We are training and supervising our machine, right? Otherwise, you have a completely unsupervised learning. You just provide pictures. You don't tell the machine whether or not this picture corresponds to a dog. We want the machine to discover itself whether this is a dog or if it's not a dog. Or you have the reinforcement learning. Well, we are supervising the machine, but in a dynamical way. As far as we get new information, new data, you supervise the machine. So it's not a static supervision, it's a kind of dynamical supervision. So those are three different ways that we want to pursue in order to train the machine. What kind of task can you ask the machine to perform? The first one, classification, is the one that you have already seen, right? You have a finite set, and I want to provide a label, right? Recognizing if a picture is the picture of a dog or of a cat, or recognizing, for instance, if you have a picture from a radiological department or division in a hospital, if you have pictures from the brain, you want your machine to recognize the presence of a tumor in the picture. And in case there is a tumor, which kind of tumor among very many different kinds. So this is classification. The second one is regression. You have a distribution of data and you want to find a model that somehow reflect the behavior of those data, right? Like, for instance, when you say weather forecast. But you have other task clustering. You want to splitting a given set of data into subsets according to a different criteria, or using a recommendation system. When you want to recommend, you see you have all these commercial on Google where they recommend us to buy shoes or books, right? They want to somehow find common characteristics in a given set of potential buyers and recommending specific actions for those buyers. And then you have others, say. So you may have different kind of tasks, but perhaps the most commons are classification and regression. So the model. I told you before that the model is basically the mathematical algorithm that replaces the behavior of our brain, right? Now, you have many different ways, many different models. I will not insist on those, on all of them, but here you find some names: linear model, polynomial, decision trees, random forest, and maximal margin classifiers, support vector machines. But today, very likely the most successful ones are the artificial neural networks that I've already mentioned before. So how do they work? Remember that artificial neural networks are mathematical models that consist in associating a specific input, a given output. So you have data, experience, and you want to find solution or recommendation or classification, say. And they imitate the behavior of the neural networks, biological neural networks. So how do they work? This is a very simplified representation of their functioning. You know, scientists have tried to introduce mathematical models of neurons since at least 80 years. And actually, this was done by neuroscientists at the very beginning, producing mathematical objects that were able, at some extent, to reproduce the behavior of neurons, biological neurons. So what is a neuron, say, a biological neuron doing? Well, it's receiving information for the neighboring neurons, elaborating this information, and transmitting it through, say, dendrites or axons to the other neurons. So basically, they are input, elaboration, and output. And this is a mathematical neuron, right? This virtual object. Of course, there is nothing physical here. There's nothing material. It's just a mathematical representation, right? This is an object, a mathematical object. It receives information from its neighbors, and information are under the form of numbers. Here, just for simplify, I've been indicating x1, x2, x5, say. These are real numbers. Then these neurons make some operations to imitate the operation carried out by biological neurons. And those operations are mathematical operations, actually. And they are actually simple. To some extent, for mathematicians, they are simple operations. They are a linear combination between the input values through weights, parameters that should be identified, plus a bias. And then, instead of taking this information and passing this information to the other neurons, you apply a certain function that is called an activation function. And you want to decide whether or not this information is relevant for the other neurons. So this is what every single neuron does. Now you have a series of neurons. See these blue elements here. All those are mathematical neurons. And they receive information. These are the input data. And they return answers. And these are the output data. So in the case of the dog, see, those are the orange ones are the pictures that you provide to train the machine. These neurons are mathematical objects that are all connected together, and the output is either 1 or 0. 1 is a dog, 0 is not a dog. Of course, in more complex situations, you have different type of inputs and different type of outputs, but the idea is the same, right? So an artificial neural network is a series of layers of artificial neurons, and every neuron, every mathematical neuron is somehow replicating the behavior of the real neuron. Now, what is surprising is that in our brain, we have very many neurons. Biologists estimate that we have 10 to the power 15 neurons. 10 to the power 15 means basically 10 to the power 6 and 10 to the power 9, meaning million of billion of neurons. And you have even more axons, connections between neurons. And here, those networks are relatively simple. In some cases, they consist of order of, say, 10 layers of neuron. And every layer has order of 5 or 10 neurons, say, or in all 100 neurons, rather than 10 to the power 15. And still, they are, in most cases, extremely effective in addressing specific tasks. That's a kind of, I would say, mathematical miracle, right? So the point is, how come that a simple structure like this is capable of imitating an hyper-complex structure, biological structure, like the one that we have in our brain? And of course, mathematicians are striving to understand why this is possible and how this is possible. And we're just midway. I mean, this is a new type of science. Artificial intelligence is there since 70 years, but the interest, at least from the mathematical side, is relatively recent, because it's only recently that we have been such an explosion of artificial intelligence algorithms. It's only recently that society has been involved with this issue, and this has come to a kind of public discussion, not only in university labs, say. So can we understand today why artificial intelligence algorithms are often so successful. And I will not go too much into mathematical details, but I would like to give you a flavor of that, right? So you have to set up the problem. And actually what we are trying to do here is to find a way to represent a function that goes from an input to an output. In a general sense, input means available data, meaning experience. Output means an action, right? So we want to represent this function that is only available through data in a discrete way by a mathematical object, mathematical function. And of course, you have to take into consideration this fact. It's an approximation problem going from a function that is very complicated and not known, and approximating it by a mathematical function, which is the one determined by the neural network, say, and I want to make sure that this is a good process. And basically, we can identify 3 possible sources of errors. When we approximate an exact process by an approximate problem, we make errors. And here we have 3 different kinds of errors. The first one is what is called the approximation error. How rich is our neural network to represent any possible data distribution? The second one is it's called generalization error. We train our network using specific set of data. Remember the 100 pictures of dogs or not dogs, say. How can we generalize by representing data that we have not seen? We give a completely different kind of dog, never seen before, and you pretend our model to be able to recognize that this is a dog, even though it has never seen, our model has never seen those type of dogs. Those are the generalization errors. And the third one is that we are approximating a function and we find the parameters by minimization algorithm. We are solving a minimization problem in a very high-dimensional Euclidean space of very, very, very many dimensions. You will never be able to find the exact minimum. You will only be able to approximate this minimum. So this is a third type of error. So if you can control all these 3 types of errors, we can say that we control the global errors. And this is the very difficult part. So we skip all the mathematical details, but I would like to give you only the flavor of this analysis. What you end up with this analysis is that the deeper the network, deep networks are those with very many layers of neurons, right? Shallow networks are those with a single layer of neuron. This is a shallow network, and those are deep neural networks. So the deeper the network, the better, in the sense that our model can represent many more functions or many more distribution of data than using a shallow network. That's a very important point. And, but there are many, many different points here that are really triggering mathematicians and computer scientists and that are trying to understand why you have such a great performance, even though the problem is so complex and so obscure, say, from a mathematical standpoint. In particular, there are some apparent mathematical paradoxes. Of course, they are not paradoxes. They look like paradox because we cannot yet understand them. But as far as we go on, we'll be able to better understand those behavior and then to shed more light on this. One is why you don't have overfitting. And that's a problem for statisticians. When you use very rich representation in your model, you may have overfitting. You may have models that are very good in describing the distribution of data, but they are very keen to follow the noise, and then they will not be able to generalize. Here, we are using artificial neural networks with very many parameters, very rich models, and still we avoid overfitting most of the time. This is something that is not yet explained, but it's a positive result, but without a clear explanation. Why deep architectures, deep neural networks are more effective than shallow neural networks? What makes deep architecture better and more effective than a shallow neural network? Well, when you use partial differential equations, you are facing what is called the curse of dimensionality. If you use high-dimensional partial differential equations, the computational burden increases, and very often you cannot solve the problem because the complexity is so high that it's not affordable. Here it seems that artificial neural networks are good in addressing high-dimensional problems as well. This is another not yet understood property. The other one, we are minimizing a problem. We're minimizing a function, actually a functional, and this function is not convex. Convex functions, like in the parabola, say, have only one minimum. Non-convex functions have many minima, say. And it's very difficult to find the minimum of non-convex functions. So still here, these algorithms are good to find good minima. And then the last one, which is perhaps the most critical one. Can we understand why those methods are so effective in general? Can we explain why they are effective? Can we explain which are the data that are more relevant to reach a certain decision? Now, the issue of interpretability and explainability are extremely important. And everybody is scientists are now trying to find explainable to generalized models to explainable, what is called explainable AI. Being able to explain what you are doing. If you are a doctor and you have a patient and use an algorithm, an artificial intelligence algorithm, to analyze the data of this patient, and this algorithm end up with a suggestion. Could be, say, a new therapy or proposing a surgery, right? And if you are a physician, you are not able to explain your patient why you are suggesting him or her that specific procedure, you are not credible. If you are a judge, right, you have to judge some cruel event, and in the end, you end up with an artificial intelligence algorithm with the right sentence, but you are not able to explain people why you have been reaching that conclusion. That's a big issue, right? And for scientists, not being able to explain why a certain algorithm, a certain approach works, that's a very big limitation. So we need to find a way to overcome this limitation. Interpretability is the degree by which a human being can understand how an AI system makes its decision, and explainability is why a model gets to a certain decision, right? And those are very big issues. And I would like to make a comment here. Well, it's not the first time that in science you have, say, methods of discoveries that cannot explain completely. You think of gravitational waves. It took about a century to end up with a complete theory of gravitational waves. If you think to statistical mechanics, for instance, well, still, those are theories that have been producing fantastic results over the years, even though physicists or mathematicians were not able to explain them completely. And this is also the case in the case of artificial intelligence algorithms. So I've been comparing a very well-known approach, which is called least squares. This was invented by Gauss in 1801 to find the motion of the asteroid Ceres, say. It's a way to, it's a regression way, right? You have a distribution of data, and you want to find a law that is representing this distribution of data. Now, this is very simple. Everything is very clear. This sometimes, even today, is called the machine learning algorithm, because your algorithm has to be learned by the machine by finding the right parameters. This all is very clear and is very human-driven. Now, if you compare this with machine learning algorithms, you see that all the comparisons are in favor of least squares, unless the last one. The last one is the learnability, right? If you have a distribution of data of a process that you don't know yet, if you apply least squares model, you have to provide a guess, a hint on how this model will behave. I mean, this is our ansatz, right? We have to say that this is a parabolic, you expect a parabolic behavior or a periodic behavior or a linear behavior of a given type. Here in machine learning algorithms, you don't have to make any guess. The algorithm will be able to extract the right behavior. So you are extracting knowledge, even though you are not yet able to explain why, right? So the fact that a model is not explainable, to me, does not mean that it's is not worth being investigated and being considered seriously. So I think that we are at this very stage where you have those models, many models that produce outstanding results, even though scientists are not yet able to explain why this is the case. To me, this is just a stimulus for investigating deeply and deeply, more, say, in a deeper way, and try to extract an analysis that sooner or later, an explanation that sooner or later will be available, actually. I will move to the end, toward the end. I told you at the very beginning that you have two columns, two branches. One is the one of the natural knowledge, right, anchored on science, on the scientific representation of certain physical problems with a mathematical understanding, and the other one is only driven by data, with no knowledge, with no theory, right? Can we merge the two of them? Well, this is the way I see the story, right? And after Newton and Galileo, you know, the temple of science have had two big pillars, the theory and experiments. You look at, you make experiments, we try to make a conjecture, so a theory, and then we want to prove it or to disprove it. And since the last century, we also have computers, so we can carry out simulations, numerical simulations. So the temple of science has been, you see, based on three pillars until recently. And now you have artificial intelligence or data-driven algorithms, and they tend to regard this as being the new pillar, right? The fourth pillar. That is not alternative to the other one. It's just using in a, working in a complementary way. It's a cooperation, it's not a competition. It should be regarded as cooperation. And this is what is called scientific AI, or scientific machine learning. So what is scientific machine learning? This is one definition. It's an interdisciplinary field, which is empowered by the synergy of physics-based computational models, those based on theory, and machine learning algorithms for scientific and engineering applications. And there are many, many different ways to have the two approaches interacting with one another. And to me, in 10 years or so, we'll no longer talk about artificial intelligence as we talk today. We will just talk about enhanced intelligence. Artificial intelligence will empower our natural intelligence, but they have to cooperate together. At the scientific level, this means having the two approaches working together. And there are many different situations where this is actually the case. Very often, you do not completely know the physical process. For instance, in the case of the heart that I've been showing you at the very beginning, when you go at the level of cardiomyocytes, you do not know the laws that allow the electrical field to be, the electrical stimuli to be translated into mechanical force. If you find this law, you get the Nobel Prize, the next Nobel Prize, just to tell you how difficult it is. Right? We use artificial intelligence to extract this type of information, not under the form of an analytical formula, but under the form of an input-output function, say. Most often you don't know data. When you use partial differential equations, you need boundary conditions and initial conditions. In the case of the heart, you don't have initial conditions. You cannot stop a patient, the heartbeat of a patient, to reconstruct the initial condition. You have to guess them, right? So you have to initialize your algorithm. You can do it by machine learning algorithms. We don't know the parameters that characterize my heart with respect to your heart, right? You have many different physical parameters that are not known, and you cannot use experiments to extract this information. This would be too costly and too invasive, right? So you have to infer by solving inverse problems to characterize these data that are missing, these coefficients that are missing. Those are examples where you see that artificial intelligence can help the solution of partial differential equations. On the other side, you can use partial differential equations to enhance the explainability of machine learning algorithms. When you want to introduce your performance measure, your loss function, you can introduce the residual of the partial differential equation if you know it. So there are many ways you can get an interplay between machine learning algorithms and natural intelligence under the form of, say, model equations or a physical understanding. Now, there are many, many different new developments also for the mathematical side. The idea now is to introduce what is called operator learning. So you want your artificial intelligence algorithm to be able not only to learn the distribution of data, but to learn the physics behind, the differential operator behind. And this is a big step. You go from finite dimension, that of the data, to infinite dimension, that of the infinite dimensional spaces, like subway spaces, for instance, for partial differential equations. That's a big conceptual step. Now, let me finish by just, because time is over, by mentioning some of the big issues that are still open in artificial intelligence. Now, I'm not talking about only the scientific problems. I tried to address the scientific problem before. Now, these are problems for the society at large. We don't have a supranational governance, and we need it. We need it because this is a wild field today. We do not have enough skill from our universities. We're not producing enough or forming enough students that will be asked by the society with this type of expertise. We have a concentration among a few key players, the big tech. Those like Microsoft, Amazon, Meta, Google, and so on and so forth, OpenAI, who have data, right? And data is the actual fuel of the most important fuel for those type of algorithms, because those algorithms are not based on theory, on theoretical knowledge, they're based on experience, on data. So there's a big concentration, and of course those companies, they have their own agenda, their own interest, and, which is not necessarily the interest of the society at large. We have the point, you need an AI jurisdiction. You need to find where are the responsibilities when you use or misuse specific algorithms, right? You have privacy, confidentiality issues. I mean, if you use large language models like ChatGPT, this has been trained with all what was available in the internet. So you may, for instance, if you think in terms of medical images, I mean, taking medical images coming from different hospitals, right? And those have been used to train. Or if you look at the art, right, they are using picture paintings and text without paying any fee for them, right? You have environmental sustainability. Every time you make a prompt in ChatGPT, well, the amount of energy that you spend behind the scenery is equivalent to the one that is necessary for 10 Google interrogations, right? If you generate a picture with ChatGPT, well, the energy that you spent is equivalent to the one that you need to charge your cellular phone, just to give an example, right? And you know that there's a proliferation of data centers, and those are extremely energivores. So the curve of increase of energy spent for the data centers to use AI algorithms is not sustainable. I mean, it's expected in 2026, the amount of energy spent only for AI algorithms is, roughly speaking, equivalent to the one that the entire Italy with 60 million inhabitants will use for all its energy, needs. So you understand that this is not sustainable on their own terms. That's why people are moving toward different kind of paradigms. And there are many different new ideas, One is to use quantum computers or neuromorphic computers instead of the classical von Neumann computers. And the other one is working at the, algorithmic level, And again, you have heard that on the energy side, I mean, those big companies are trying to empower this data center with nuclear reactors in order to save electrical energy. But it's not only a matter of electrical energy, it's also a matter of water. You have to cool the systems. And of course, there's the pollution. So you see that the sustainability issue is extremely important here, and it calls for a major, reformulation of the approach, And this is, well, of course, I don't have time to go through those things, but this is the end of my talk. And I try to summarize these concepts in a non-technical way in this new book. If you are interested, you find some of the considerations that I made today and, of course, developed in a more narrative way. So thank you very much, and if you have questions, I'll be glad to answer your questions.